All right, so to understand polar or nonpolar, this would be a nonpolar molecule because all the elements around the center atom are the same and there are no lone pairs. I emphasize the and because let's say I change this molecule to include a lone pair of electrons, and this molecule technically wouldn't actually exist, but let's pretend like it does. This would be polar because you have that lone pair of electrons that would end up creating what we call a dipole. The dipole is this idea where you get a partial negative charge and a partial positive charge on that molecule. The partial negative charge is because of the lone pair of electrons. Electrons are negative, giving you negative charge up here, and then a partial positive down here. Okay? So that's your basic idea of polar, nonpolar. And I think we were doing a decent job of that, last class. So we're building upon that, and that's what this slide is just trying to review. An example of a polar bond I showed you was oxygen to hydrogen. Oxygen is more electronegative than hydrogen, so this part of that bond will become polar. It gets a slight negative charge. This part of the bond gets a slight positive charge. Okay? The more electronegative atom, the higher electronegativity, that means this molecule wants the electrons more, and that's why it's going to get that slight negative charge. A fancier way of saying that is electron density. Electrons density. How much do the electrons favor this atom? So the reason why the oxygen is a bigger sphere over here is because it has a higher electron density. That comes from the higher electronegativity. Higher electronegativity equals a higher electron density. Okay? So there you go. Any questions about this? That's it. You've seen something like this before. Here. So not nonpolar or ionic. Basically, like if you had NaCl, there comes a point where polar, like you get the positive and the negative charge of the molecule, there's an unequal sharing of electrons. At some point, the sharing of the electrons becomes so unequal that it becomes an ionic bond. So I just want you to understand, like, there's nonpolar where the electrons are shared equally. Polar, the electrons are shared unequally. Ionic, there's a complete transfer of the electrons. So ionic, that's when you add the metal plus a nonmetal. So if I show you any sort of molecule where it's a metal plus a nonmetal, you'll automatically know that's got to be an ionic bond, not polar bond. Any questions about that? Okay. Get my cursor over here. Okay, so thinking about like the whole molecule level of things, if we look at water, water is H2O. There is one oxygen atom bonded to two hydrogen atoms. Okay? On the last slide, we talked about one of these, we isolated one of these oxygen to hydrogen bonds. And I said that because oxygen is more electronegative than hydrogen, oxygen gets the partial negative charge and hydrogen gets the partial positive charge. So if you have a second oxygen to hydrogen bond, you would get a partial positive on this part of the molecule and even more partial negative on that part of the molecule. And when you did that polarity simulation a couple class periods ago, you would have gotten that overall the dipoles would have looked like this. Those would be the bond dipoles. And then you would have seen the molecule dipole would look something like this. Now, on your test, I'm not going to make you draw these dipole arrows. You just need to understand what they're trying to say. The head of the arrow is pointing to the negative charge. The tail points to the positive charge. We talked about that a few class periods ago when we first went over this. The point is, this is a polar molecule. There is a negative and a positive end. Okay? A lot of the properties of water comes from the fact that water is polar. All right. So what can happen then, and this is getting to intermolecular forces. To understand intermolecular forces, think of the interstate highway system. Interstate highway. What is the difference between the interstate highway and a normal highway? Have you ever thought about that? Sure, yeah. It goes through multiple states. Inter has something to do with like going like between things or across things. Interstate, it's a highway that runs through multiple states. That is different than like a normal highway that might just run only through Virginia or something. Okay, so intermolecular forces are forces between multiple molecules. So here you see we're looking at multiple water molecules, and we're looking at on this slide hydrogen bonds. So hydrogen bonds is one of your intermolecular forces. So building upon this idea of water being a polar molecule, what happens is this oxygen we said has a partial negative charge. Okay? The hydrogen gets a partial positive charge. We know that opposites attract, right? So you should have heard of a hydrogen bond before, and especially like freshman bio, you kind of vaguely learned about it. What the hydrogen bond comes from is the fact that you have that partial negative and that partial positive on multiple water molecules. This creates a force here. This is not a bond. Well, it is a bond, but it's not a bond in the sense of like there's a sharing of electrons. There's no sharing of electrons here. There's an attraction here. Okay? And the overall attraction of this is what gives surface tension. So surface tension is like, when it's summer and you're laying on a raft in the pool, this is why you can do that. These hydrogen bonds is why you can do that. Okay? The hydrogen bonds is also why you get like the meniscus. If you like look at water in a beaker, it gets that little dip shape. That will come from hydrogen bonding. Now, you need to understand how to recognize a hydrogen bond. And to recognize a hydrogen bond, I want you to think of fun. But like, imagine fun, but you don't know how to spell very well. And so you spell it fawn, F-O-N. So a hydrogen bond happens when it is a hydrogen atom, because it's a hydrogen bond, bonded to fun, fluorine, oxygen, and nitrogen. So if you see hydrogen bonded to fluorine, oxygen, or nitrogen, that's when you can get the result of a hydrogen bond. Now, this oxygen to hydrogen bond, that's not a hydrogen bond, even though it's a hydrogen bonded to oxygen. It's when you get multiple molecules that have hydrogen bonded to oxygen or nitrogen or fluorine. I'm going to say that one more time. It's a very important detail, and it's something that confuses people. This oxygen to hydrogen bond is not a hydrogen bond. It's just a normal bond. The hydrogen bond is when you get multiple molecules, intermolecular, multiple molecules that have the hydrogen bonded to an oxygen or hydrogen bonded to nitrogen or fluorine. It's that attraction between the negative and positive ends of those molecules. Okay. So any questions on that? DNA and proteins have a lot of hydrogen bonds. Hydrogen bonds are really important in biology because they're strong, but they're also flexible. Okay? All right. Moving it on. Here's some other examples of hydrogen bonding. So, water we just went over, but you could have water and ammonia. So I said fun, but fun, right? Nitrogen bonded to hydrogen. So this is, again, this specifically is not a hydrogen bond. This is the hydrogen bond. The hydrogen bond is the attraction between the partially positive hydrogen of one molecule and the partially negative part of the other molecule. Okay? Another example of hydrogen bonding, notice how it's hydrogen with fluorine. So you get between multiple hydrofluoric acid molecules, you get that hydrogen bond, that dashed red line. It's a partial attraction. There's not actually like a sharing of electrons, but there's an attraction there. And then methanol, more oxygen to hydrogen, but it can look a little bit different. What's interesting about methanol is like you can have this portion of the molecule having carbon to hydrogen bonds, but because you have a portion of the molecule that has oxygen to hydrogen, you still will get hydrogen bonding at this portion of the molecule. The end portions of the molecule don't do hydrogen bonding, but you do get a portion of the molecule that will have hydrogen bonding. Okay? You got questions on that? All right, cool. So that was the first kind of intermolecular force. So it's hydrogen bonding. So the second kind of intermolecular force is called dipole-dipole. So we talked about dipole a couple class periods ago. Di means what? Two. Pole is referring to the partial positive and partial negative charge molecules can get. So dipole-dipole is basically the same idea as a hydrogen bond, but it's not hydrogen bonded to fluorine, oxygen, or nitrogen. It would involve, a lot of times it can involve hydrogen, but it can be hydrogen bonded to other elements that aren't fun, right? Like things like chlorine or things like bromine or something. Or it doesn't even have to always involve hydrogen. It can involve other bonds that would be like a polar bond, like carbon to chlorine. If you had like multiple like let's say we had a molecule like this. Let me give you an example. Let's say you had this. Is this a polar or a non-polar molecule? Polar, because all the elements around the center aren't the same. They're almost the same, but fluorine is different than chlorine. So what happens is this part of the molecule gets a partial negative, this part gets a partial positive. So then what could happen is, let's say you have multiple of these molecules. So let's say you have a second one of these molecules. So here, this partial positive and that partial negative, they could form a dipole bond with each other, right? It's similar to the hydrogen bond, but it's just an attraction between the negative part of the molecule and the positive part of another molecule. Okay? It's not as strong as the hydrogen bond, but again, it's a similar idea. It's that partial, that's the attraction between the partial negative and the partial positive of a polar molecule, of two polar molecules. Okay. So moving it on. So here's another example. So if we look here, carbon to oxygen, that bond is a polar bond. Oxygen is more electronegative than carbon. That's why oxygen gets the partial negative charge. Carbon is not as electronegative. That's why carbon gets the partial positive. So if you line up multiple of these molecules, the partial negative of one molecule wants to line up with the partial positive of another molecule. And this dashed line that I'm drawing, that is the dipole-dipole force. So these dashed lines represents a dipole-dipole intermolecular force. Okay? Similar idea to a hydrogen bond. It's just not as strong, but there's an attraction here. These molecules are slightly attracted to one another. Okay. Make sure I said everything here. Remember the word electron density? So again, it's kind of a fancier way of saying the electrons are more attracted to the oxygen than the carbon. Oxygen has the higher electron density. Okay, so then the third and final kind of force I want to talk about is called van der Waals. And this one has multiple names. You'll hear it called van der Waals, after the scientists discovered it, van der Waal. Dispersion forces, or you'll hear it called London dispersion forces. All three are like acceptable synonyms, but you'll hear it said like either way. And to understand London dispersion or van der Waals or dispersion forces, let me ask you this. If I flip a coin, what are the odds that I get heads or tails? 50%, right? We all agree. If I flip this coin 10 times, and I don't know if you've ever done this, but let's say I flip this coin 10 times, there's actually a pretty good chance I'm not going to get 5 heads and 5 tails. Why is that? Does that mean there's not a 50% chance of getting heads or tails? going to say that again because understanding this is like key. You got to understand this example. We all agree there's a 50% chance of getting heads or tails. But if I were to flip this coin, let's say, oh, the Super Bowl is coming up, and they're like, the home team, or like heads is flipped on the Super Bowl coin 70% of the time. Does that mean the Super Bowl coin, there isn't a 50% chance of getting heads or tails? Why? Somebody explain to me. What's going on there? Ever? Yeah.
The coin might not be perfectly.
Oh, okay. Yeah, you're saying like it favors one. But let's assume like this coin is perfectly balanced, and I flip it 10 times, and I get 6 heads and 4 tails. Does that mean that like there's actually not a 50% chance? Nora, go ahead. Yes, right. It's about the sample size. If you only flip it 10 times, and I invite you to try doing it, it's a very good chance you won't actually get 5 heads, 5 tails, but that 50% is assuming a large sample size. You got to do it like, 1,000,000 times, and the more you do it, the closer you'll get to 50-50. Okay? Now, what that has to do with this is, when we say a molecule is nonpolar, we're saying overall, on average, the electrons are evenly spaced out. And that's what you see here. On the long-term average, these electrons are evenly spaced throughout this molecule. Okay? But in an instantaneous moment, if you were to like, at any one moment, zoom in on that argon atom here, there might be a slight chance that the electrons are favoring this part of the molecule versus this one. There's no necessary reason why it would, just like there's no specific reason why I might get 7 heads and 3 tails if I flip this 10 times. It's just by chance. Now, what happens, what we call that is a temporary dipole. It's a dipole. You have a partial negative and a partial positive, but it's temporary. If you just give this another few seconds, this molecule will become like this. But let's imagine that you get this temporary dipole. And then what this could do is, if you have a second argon atom here, and this second argon atom, its electrons were evenly spaced out, but what would happen if you get a temporary dipole here? What's going to happen to this molecule? Think about it. This molecule gets a partial negative, a partial positive charge, just by chance. What would happen to this molecule that's right next to it, that does have its electrons evenly spaced out? Think of the wave in a stadium. Sure?
Would it pull from the original argon?
Yeah. So because there's a partial negative charge here, electrons want to get away from this negative charge. So these electrons are going to move over here to get away from the electrons here. So this molecule will get a partial positive here and a partial negative there. Really try and get it's understandable. Think of the wave, right? I do this and then you do it because you see me do it. This one starts the wave. This molecule, by chance, gets a temporary dipole. The electrons favor here over here, just by chance. Because there's a negative here, that then is going to create a positive on the neighboring argon atom, which gives this one a partial negative. And then if you have the entire sample, the next atom will get a partial positive and a partial negative, and that keeps going throughout the entire sample. So in other words, you can get intermolecular forces in a nonpolar material just by chance. And it exists for like a very short period of time, and then it'll go away. Any questions about that? It's understandable. It's kind of a goofy idea. Let me keep moving forward, and let me show you this example, and maybe it might make a little more sense. So here's another example. They're showing a helium atom. Helium, the electrons in helium are on average evenly spaced out, but again, by chance, just like when you flip that coin, you can get, just by chance, the electrons favoring one end of the atom over the other. That would give a partial negative over here and a partial positive over here. The next helium atom in that sample, because by chance you got the negative here, its electrons are going to get away from this part of the molecule, move over here to get away from those electrons, creating this dotted red line there. That is your London dispersion force. And that can spread throughout your material, giving you like that slight attractive force. Now this is another detail that students kind of forget about. All molecules have van der Waals forces. Okay? Even if you have a sample of water, all materials are going to have just by chance an unequal sharing of electrons. But in water, you don't notice the van der Waals forces because hydrogen bonding is so strong. Geez, what would be a good example of it? It's like, I don't know. It's the best example I can think of off the top of my head, but like if you ever watch like a sports game and it's like, it's like, oh, why did one team win over the other? And like, let's say it's like somebody has like the best quarterback in the game or something, and you would be like, oh, they won because they have such and such quarterback. But what if I was like, yeah, but that one guy got that one tackle, and you'd be like, yeah, that tackle I guess was good, but like that isn't the reason why they won. The reason why your raft is floating on water isn't because of the van der Waals forces, even though those exist in water. It's because of the hydrogen bonding. The hydrogen bonding is so strong in water, it overpowers the van der Waals forces. But all molecules will have the van der Waals forces. So, in other words, the only time van der Waals, the London forces, are relevant are when you have nonpolar or larger molecules. So molecules that don't show the dipole-dipole or hydrogen bonding, that's when they're going to have the van der Waals forces being shown really strongly. Okay? All right. An example of like how are van der Waals forces kind of used? Geckos. If you're like, you see like how geckos can like stick on like windows and walk around and stuff. And you're like, what's going on there? How are they just like walking on glass? Van der Waals forces. Geckos will have, if you look at the very like their little paws, I guess you could say, they'll have these little tiny extensions, and each of these little tiny extensions will have themselves little tiny extensions, and those extensions can utilize that temporary dipole that can exist on any one of these little extensions. And that will then create a slight attraction between itself and the glass, allowing it to walk across the glass. So, I don't know, kind of cool. All right. Shout out to, you may know Stella. She's a junior now. I taught her last year. Stella came up with this idea. And so this slide brings it all together. So all molecules, as I said earlier, all molecules will have, whether you are polar or nonpolar, every molecule will have van der Waals or London dispersion forces. But within that, only some molecules will have dipole-dipole forces. Okay? Those molecules are polar molecules. Only if you're a polar molecule will you get dipole-dipole forces. Hydrogen bonding is a specific kind of dipole-dipole force, right? That partial positive, partial negative, creating the attractive force. So only if you are a polar molecule that has hydrogen bonded to fluorine, oxygen, or nitrogen, remember fun, but with an N, only if you are a hydrogen bonded to one of those atoms do you show hydrogen bonding. But hydrogen bonding, if your molecule has hydrogen bonding, you will also show dipole-dipole and show van der Waals. Okay? All right. Here's an example of like a test question you might see. Select all the molecular forces present in a liquid sample of each compound. So, looking at this one, this molecule here, which forces do you think it would have? Basically, what we see here is you see a bunch of carbon to carbon or carbon to hydrogen bonds in that first molecule. Would you have hydrogen bonding if you have a molecule that has carbon to carbon or carbon to hydrogen bonds? No, there's no fun there. You don't see hydrogen bonded to fluorine or oxygen or nitrogen. So that wouldn't be one. Would you see dipole-dipole interactions? In other words, is this a polar molecule? Or is it nonpolar? This would be nonpolar. You don't see any scenario here where you have like carbon bonded to like a really electronegative atom. You just have carbon to carbon and carbon to hydrogen bonds. So it wouldn't be dipole-dipole. So it can only show the dispersion forces. It can only have that like slight chance that you get a partial positive and a partial negative. Okay? Now jumping to this middle one. Here, would you have hydrogen bonding? Hydrogen bonding, do you see hydrogen bonded to fluorine, oxygen, or nitrogen? No. Okay, so you can mark that one off. Do you see dipole-dipole interactions? In other words, is this a polar molecule? It would be a polar molecule. Right here, that carbon to oxygen bond, that would be a polar bond. So this is going to create that partial negative and the partial positive, that dipole that we've shown before. And you could have multiple of those molecules having that dipole-dipole interaction. So that would be true. Would it show dispersion forces? It would, right? If you go back to this, if you show dipole-dipole, you will also show van der Waals or London dispersion forces. I spelled dispersion wrong, dispersion. That's not how you spell dispersion. Anyways, so yes. All right, coming over here. With this molecule, would it show hydrogen bonding? It would. This right here, this is an oxygen to hydrogen bond. So that would be a hydrogen bond. If you had another one of these molecules, this could then form hydrogen bonding. This could then form that partial attraction right there that we call a hydrogen bond. So that would be true. That would be hydrogen bonding. Would there be dipole-dipole interactions? Yeah, if you go back to here, if you're hydrogen bonding, that is a form of dipole-dipole. So that's true. Would there be dispersion forces? Yes, again, if you show hydrogen bonding, you also show dipole-dipole. You will also show van der Waals forces. But again, those dispersion forces aren't as relevant. They're not as strong compared to the hydrogen bonding. Okay. Last idea, last concept is boiling point and melting point. So if you look at these molecules here, they're showing, all right, this is a dipole-dipole interaction, right? You got the partial negative, partial positive. So here's the intermolecular forces between those molecules, that attraction there. In order for something to boil or for something to melt, what you have to do is you have to break all of these attractions here. You have to break all of those bonds. If you break all those bonds, then that liquid can boil. Okay? Now what that means is the stronger the intermolecular forces, we abbreviate IMF, the higher the boiling point or melting point. Meaning, if I jump to the next slide, if you're something with hydrogen bonding is the strongest intermolecular force. So the higher up you are, the stronger the intermolecular force. Hydrogen bonding is the strongest. Hydrogen bonding is going to have the strongest or highest melting point or boiling point. It's going to be the highest because the bonds, the attractions between the molecules is strongest. If you're in the middle, dipole-dipole, so like here's a dipole-dipole attraction, this would be in between melting point, boiling point. And then finally, London forces. If you're if you're something that's a nonpolar molecule where you only show the van der Waals forces, you're going to have the lowest melting or boiling point. Okay. So this is kind of a slide that brings everything together. All right, let me stop the recording.